please, Shi Li Hong, Li Guangping, and Li Jungping, please start sharing the screen, and please do the presentation. You can finish a little bit later, so please don't be pushed by the time limits. Thank you very much. Thank you. Please start.
Okay, thank you. Can you see my screen?
Yes, we can see your screen. Actually, I wanted to say that these students, they come from the Leiden University, so we are very happy that that such a good students apply to our university and do such a great presentation. Thank you.
Yeah, yes, thank you. Hello, everyone. My name is Lin Hong. From St. Petersburg State University, and the other members of our groups are Li Jiping and Li Qiong. And our group's report is about overview of methods and approaches of reinforcement learning. There are four parts of in my report. First one is overview of reinforcement learning. Second one is reinforcement learning solving method. It's about dynamic programming method and mental color method and temporal different learning. And the first is algorithm. Sorry, the third is algorithm, and there are 6 in total, namely Q-learning, SHA-SHA, DNQ, policy gradient algorithm, actor critic, deterministic policy gradient, and the last one is application of reinforcement learning. And first, let's look at how reinforcement learning works. Cat is an agent that is exposed to the environment. In this case, it's your house. And an example of a state could be your cat sitting, and you use a specific word in for cat to walk. Our agent reacts by performing an action transition from one state to another state. For example, cat goes from sitting to walking. The reaction of an agent is an action, and the policy is a method of selecting an action given a state in expectation of better outcomes. After transition, they may get a reward or penalty in return. So let's consider that Markov decision process. Markov decision making has 3 requirements. Firstly, it can detect the ideal state. Secondly, it can try multiple times. Thirdly, is the next state of the system is only related to the current state information and has nothing to do with the early state, and is also related to the current action taken in the decision making process. In reinforcement learning, the agent and the environment are always interacting. At each time, the agent will receive the state from the environment based on this state. The agent will take action, and then this action will act on the environment, so the agent can receive a reward, and the agent will reach a new state. Therefore, the interacting action between the agent and the environment is actually a sequence. So why is reinforcement learning so important?
Sorry,
In
sorry,
generally,
could you
okay.
please go back for a second? So
Okay.
why we introduce Markov decision process? Because now currently the model for the reinforcement learning is actually Markov decision process. So in reinforcement learning, the agent has a state, has an action, and has a reward. And we have a transition function which from the state from a pair of state and action gives us a next state. And while the training, so reinforcement learning is a kind of a a training method or applied yeah, so training method. And in this training method, the algorithm needs to know which strategy or which policy in reinforcement learning is called policy is better for the problem he needs to solve. So, and the algorithm by what the algorithm is doing is actually by choosing different types of policies, means that by choosing different actions in different states, he tries to evaluate which policy is better. And by choosing different actions, the agent receives different types of different rewards, or payoff function, or objective function. So the aim of this kind of procedure is to receive more reward. So the agent in reinforcement learning is trained, or can be considered as an optimal agent if his policy gives us the highest reward. So this is kind of the idea. Yeah, in multi-agent case, we have a lot of agents and they have their own rewards. They also train how to act and so on. So please continue, please continue.
Okay, thank you very much. So why is reinforcement learning so important? The main reason reinforcement learning has received widespread attention at the moment is because it's suitable for many application scenarios and does not require a lot of expensive labeled and data like supervised learning. Compared with supervised learning, the way of thinking and the specific algorithms of reinforcement learning can better describe the process of human learning, which is more similar to the behavior of learning of living subjects. Many researchers believe that reinforcement learning is likely to lead to strong the artificial intelligence approach also aids to the charm of reinforcement learning. It's precisely because of this characteristic that reinforcement learning has received so much attention today and has become such an important research direction. And this is the algorithm flowchart of reinforcement learning. So let's talk about the dynamic program method in reinforcement learning. Policy iteration includes policy evaluation and the policy improvement. The policy evaluation itself is also an iterative operation. Every time a policy is evaluated, the initial value of the value function is the value function of the previous policy. This usually significantly improves convergence speed of policy evaluation. The action is selected according to the strategy defined during strategy evaluation, and the action is selected according to max Q and based on the value function of convergence during strategy promotion. The strategy obtained by strategy promotion is not necessarily the same as the previous strategy. Policy iterations usually require only a few iterations to converge. Then comes the value iteration part. Analyze value iteration from perspective of policy iteration. The value function update can be divided into two steps. The first is policy improvement. The policy is promoted according to the value function before the update to obtain a greedy policy. The second is policy evaluation. According to the greedy policy, select the value corresponding to the greedy action A instead S, and update the value function correspond to S. Unlike policy iteration, In the value iteration process, the algorithm does not give a clear strategy, and the value function obtained during the iteration process does not correspond to any policy. Also, value iteration does not require policy participation. It still needs to know the transition probability between states. That is, it needs to know the model. This figure is the result of value iteration, and the other picture is another between new and old value table. Let's talk about Markov policy evaluation. The Markov mental color mental color, sorry. Mental color method is also called statistical simulation method. Such use random number or pseudo random numbers to solve calculation problems different from general dynamic programming algorithms. Mental color method looks at the problem from a few perspectives, and in short, it's focused on how many samples do I need from the environment of to distinguish the best policy from the bad policy. Monte Carlo strategy evaluation use the average obtained value of multiple episodes instead of the data value function. This is a Monte Carlo model about a blackjack game. The highest point, the highest point of the value function is the best strategy. The temporal difference algorithm is a model of free reinforcement learning algorithm. It inherits the advantages of dynamic programming and Monte Carlo methods to predict state value and the optimal policy. TD prediction is the same as Monte Carlo method. There are still two parts of calculation. The first part is TD prediction, and the second part is TD control, whose purpose is to obtain the optimal policy. TD prediction is to calculate the state value. In terms of calculation time, TD is faster than Monte Carlo method. According to the formula, TD only needs to wait until it jumps to the next step to know the state value of the current state. However, the Monte Carlo method needs to wait until the end of the entire experiment to get the current state value. Because when TD calculates the value, is calculated based on current state and the next state. So there is a diversion, but the variance is small. In contrast, the Monte Carlo method is unbiased, but the variance is large. Now, okay, now we will consider algorithm about Q-learning. So Q-learning is a value-based algorithm in a reinforcement learning algorithm. Q is the expectation that taking action A and a certain moment in the state can obtain the benefits, and the environment will respond according to the action of agent return rewards. So the main idea of the algorithm is to construct the state and action into a Q tables to store the Q value, and then select the action that can obtain the greatest benefit based on Q value. So first picture is about how Q-learning makes decisions, and the second picture is how the Q table is updated. And then we have the SHASHA algorithm. And SHASHA algorithm is also Cotton algorithm reinforcement learning. Its algorithm are formula are very similar to Q-learning, but Q-learning is own policy and Sasha is own policy, so they are different. The decision making part of the Sasha algorithm is the same as that of Q-learning, and all decisions are made in the form of Q tables. In the Q table, the action value with a large value is selected and applied to the environment in exchange for rewards and punishments. That is, the calculated Q value is used as the basis of for selecting the action. The difference between the two is that the behavior update criterion is different. Will not choose the maximum Q estimated value he estimated, but directly choose the estimated Q value. So this picture is a comparison of the two algorithms. So this picture is about the application problem. It is used the algorithm of Q-learning and Sasha. Sorry. RG, Y, and B are four different places, and the rule of the game is pick up passengers at one place and then send them to another designated place. You can get to 20 points for completing a successful passenger transfer. But for every step of the taxi, you will get 1 point deducted. In addition, 10 points will be deducted for sending passengers to the one place. So yellow square represents the taxi, and the vertical line represents the wall, and the blue letter represents the location to pick up passengers, and the purple letter represents the local location where a passenger get off the taxi. When there are passengers in the taxi, it turns green. So this picture on left is a reward convergence curve when alpha equal, when alpha equals 0.4, gamma equals 0.999, and epsilon equals 0.017. The picture on the right is the result of error between the old and new tables. And these two set of charts are the result when alpha takes different values, and it use the algorithm. It can be seen that when alpha is equal 0.3, and the simulation result is very similar to the result of the Q-learning algorithm, and it can be seen that when alpha value becomes larger, the optimal solution becomes smaller, and the arrow becomes larger. The next the fourth groups is the result when epsilon is equal to 0.08. When epsilon value becomes larger and the optimal solution becomes smaller, and the fluctuation is particularly large, and the arrow becomes larger. And the fifth group is the result when is equal to 0.3. When the R value becomes smaller, the optimal solution becomes smaller, but it is stable, and the arrow becomes smaller. And we talk about DQM, and DQM and Q-learning are similar to algorithms based on value iteration. But in ordinary Q-learning, when a state the action space are described and the dimension is not high, Q-table can be used to store the Q value of each state action pair. When a state and action space are high dimensional continuous, it very difficult to update the action space to and state use Q table. So here, the Q table update can be transferred into a function fitting problem. By fitting a function instead of Q table to generate Q value, the similar state can get a similar output action. Therefore, we can think that a deep neural network has have a good effect of extraction of complex features. So we can combine deep learning with reinforcement learning. This become DQM. This is the algorithms. So there are two networks with the but different features in DQM. The main net, which predicts the Q estimation network, use the latest parameters, while the network net, which predicts the Q reality, use the parameters a long time ago. And Q and theta I represents represents output of the current network mainnet, which is used to evaluate the value function of the current state action pair. And the Q theta I minus represents the output of target net. The target Q can be solved. Therefore, when the agent takes action on the environment, it can calculate Q according to above formula and update the mainnet parameters according to those iterations. The mainnet parameters are copied to target net. This completes learning process. This chart is to change of is the change of the reward as the number of epsilon increases, and this one is the maximum value of the Q corresponding to each state and action. And this chart is a comparison of training time between DQM and DQM priority replay, and it can be seen that as if those increase, DQM priority reply requires less training time than DQM. So, okay, the next one is policy gradient. So the policy gradient is used as a part of strategy output part of the neural network. In some cases, it can be either to a distribution network or a categorical network. They are all applicable to the continuous action space. And since the reinforcement learning algorithm based on policy gradient is on policy, then this is no need to introduce a gradient algorithm like a DQN algorithm. The algorithm of the policy gradient class updates the parameters of the policy networks through gradient calculation. So the objective function is directly decided as the expected calculative reward. There are many ways to express this expected value, which corresponds to the different calculation methods of the loss function by different specific algorithm. This is the mountain car simulation program. If you play the mountain car simulation program, you will find that the VT in the mountain car simulation program look like this chart. So this picture means please pay attention to my last series of actions in this round, because this series of actions allowed me to climb the mountain, and please punish me for the series of actions I started, because these actions failed to make me climb the mountain. Yeah.
Sorry,
Okay.
could you please go back?
Okay.
Could you explain this model? This is called the environment, right? So we want to apply the algorithm to this environment. But what is the state of this environment? What is the action that can be taken in this environment? And what is the reward? What is the goal of this environment? What is
when the car climb the mountain summit, it get reward. You know, in this environment, and the climb mountain to the it get reward.
Okay, what do we control?
So what, can you repeat?
What is the action?
What problem?
What do we control?
What's action? It just to trying to climb mountain.
How?
I don't know
what is the thing that we control? What is the state in the model? What is the action in the model? I think that everyone understands that the agent is the car, right? And the goal of the car is to get up to the mountain. And since reinforcement learning is the basis for artificial intelligence, yes, so we want to understand how reinforcement learning interacts with the car to control it in order to get up to the mountain. So could you please it's very important to give this specific description of specific details. Otherwise, we don't understand why to use reinforcement learning and so on. Could you explain a little bit? Maybe in Chinese also okay.
It use policy gradients, and I think it's it also use state to give this car initial
you can use Chinese. You can use Chinese. Lin, will you be able to help a little?
OK， 呀，别乱入，你用汉语说，怎么样？
就是这个刚才老师问的是问啥，我没听太明白。
Повторите вопрос, пожалуйста. Не понимает ваш вопрос.
Что, значит, reinforcement learning основан на понятии state, состояние, action, это значит, чем мы управляем, что мы делаем, и reward. Как в этой модели определен state, action, reward? Конкретный ответ нужен, не общие слова, а конкретные.
并不是一个这个你们专业东西，我не конкретные нужно конкретные слова。他说你不要用那些大的那些宏观的词汇，用一些具体的实际的精准的东西描述一下。
就是state 是车的位置，是这个 location。
State это значит позиция машин.
对， 就是给他一个给他一个力让这个车这个左右运动，然后让他去登上这个山顶。
这个怎么说？
就是 action 是这个推车的力可以向左也可以向右，然后让他去爬这个山，然后
машина можно назад или напрямо и с помощью от других, да, можно наверху.
Ну, можно сразу поехать вперед и доехать. Почему нельзя? Почему эта задача интересная?
他说：“为什
Вперед
么你这个问
или
为
нет?
什么这个问题就是这既然往前往后，为什么这个问题你对这个问题感兴趣呢？或者这个问题兴趣点在哪儿？”
因为他使用了这个 policy gradient，所以我拿出来介绍一下这个问题。
这使用了什么东西啊
就是这个
？policy
policy gradient
啊
yes.
Потому что в этой проблеме исправили policy gradient, поэтому он хочет просто объяснить. Это пример.
Я понял, но мы должны понимать конкретно, как работает алгоритм. Иначе понимание, что такое policy gradient, не поможет. Нам надо знать, чем алгоритм управляет, что он делает в этом конкретном примере. Это важно. Без этого сложно понять.
就是你这东西不是在动吗？在算法里面如何让它动？在算法的意义上是如何做到的？我不太懂你研究的东西啊。这个问题是你自己拿这个东西来举例这个 policy gradient， 但是他呢很想知道你到底是如何让它控制的，就是 policy gradient 到底是如何控制它的，对不对？
对，因为它这个是就是 action state space 是连续的，所以说就是因为这个 PG 比较适合用在这个连续的环境，然后这个车就是你给他一个这个初始的，就是我不知道怎么去说，就是你给他一个初始的这个这个值，也就是让他去就是学习的方向就是目标函数的梯度方向。
这个你有代码吗？
现在可能展示不了这个代码。
Сложно объяснить, потому что не очень понимаю его исследования. На самом деле здесь нет алгоритма, поэтому он не может объяснить. Он просто сказал, это 你这个算是个黑盒吗？
不算，因为它还
很重要是吧？
不
就是这个算法还是你研究？
算黑盒吧，算黑盒吧，应该算黑盒，对，算黑盒。
Он сказал, это почти black box.
Okay, no problem. Okay, so it's a kind of black box. So it's a kind of ready to use environment to test reinforcement learning algorithm, right? But I suggest you in future when we do this kind of presentation to explain directly in this environment what is the state, what is the action, and so on. I think in this environment, action is how fast you try to run the wheels. And since I think it's not a very simple model, I think here from the speed of the wheels, you do not directly get a good result. So maybe the policy could be like this: to go back, yes, to go back a little bit, and then go forward. So in this example, it is not very precise how to drive this car, how to get up to the mountain. So I think next time it's important to introduce this kind of details because to show why it's important. Okay, thank you very much. Thank you. Please.
Okay, thank you. So next is actor critic. There are there are two neural networks in the actor critic algorithm framework. One neural network is called actor input state output action, or the probability of each action. The other neural network is called critic input state and action output list action state pair the Q value. This algorithm combines the methods of policy gradient and the function approximation. So since critic is a value-based learning method, he can perform a single-step update and calculate the reward and the punishment value for each step. Then the two are combined. The actor chooses the action, and the critic tells the actor whether the chosen action is appropriate. In this process, iterating to get a reasonable probability of choosing each action in each state. Critic also continues to iterate, constantly improving the rewards and the punishment of each action selected in each state. And the inverted Pandora problem is a classical problem in the control literature. In this version of the problem, the Pandora starts at a random position, and the goal is to swing it upward so that it stays upright. This chart is about total moving reward chance state. Okay, then we talk about the last algorithm, deterministic.
Could you go back a little bit?
Okay.
So I want to comment on the previous environment. Can you go back? So that's a very classical environment, and I can say example or model for reinforcement learning, but not only, also for the control theory. So actually, sometimes you can see a very good connection between the control theory and reinforcement learning, because the output, the result of the reinforcement learning algorithm is a policy which is a function of state that gives us an optimal result or optimal reward. Yes, and in control theory, the analogy is the closed loop strategy. This kind of strategy is a function that for every given state X and time instant T gives you the control that eventually will give you an optimal value for the objective function. So you can consider how these two things are related to each other. Control theory with the control and objective function and state, with reinforcement learning with the reward state and the policy, and also game theory with the payoff function, state also, and strategy. All these things are connected. And in this particular example, what you can see, it's very classical. What you can see is that you have a pendulum, and the pendulum wants always to go in here or in here. So it is connected to a wall or someplace in here. And what we want to do is we want it to be up, to be in here. But this kind of position of a pendulum is not, it's not stable. And any kind of random perturbation to the right or to the left, some random thing, noise, any kind of physical perturbation, can cause that the pendulum will go down eventually, very fast, right? So we want a kind of stabilizing control. We want to control it every time up, to be up, yeah? So this kind of task is it's kind of more of kind of educational task. but there are a lot of stabilizing problems in the world, such as stabilizing for a plane, stabilizing the signal, stabilizing a rocket. We need to stabilize something all the time. When we have some random perturbation or noise in the physical world, we need to know how to do it. And this is a kind of example how it can be applied. And the reinforcement, the state of the model is actually the angle. So the angle of where the pendulum is now, it's the angle. And the action, our action of agent, the agent now is a stabilizing agent. He wants to stabilize the pendulum, is to try to push pendulum to the left and to the right in order it to be stabilized. And the reward is actually, I think the reward can be modeled different ways, but the essential meaning is the reward is of how the current angle of the pendulum is far away from being up. This is very simple. And what you can see is that we try to maximize the reward. We want the angle of the pendulum to be as close as possible to the upper value. Yes, we can even add some random noise. We can even push pendulum, yes, by some manually push pendulum, and then reinforcement learning will try to put it up. I think next month we will add some kind of video explanation of how it works, because for all of this, of course, we have the code. It's not only the presentation. Everything was done by this group of students. They're very good. They performed all the simulations. Actually, what they're doing is currently they're finishing their educational phase of their master thesis. So they kind of, learn different types of online courses and reading books, and yeah. So this is it. So you will see all the things, and if you're interested in the materials that we use, actually we will be very happy to share it to you. Okay, so but that's a kind of an educational example. Thank you very much. Thank you. Please continue. Please continue.
Thank you very much. Okay, then we talk about the deep deterministic process gradient. DDPG is labeled the DQN algorithm in continuous action space, many of which can be found in DQN algorithm and its various variants. At the same time, DDPG is different from the above mentioned various algorithms. It's an off-policy algorithm, so it requires experience, traceback, and adding random noise. Since the very function of DDPG estimates the neural network estimates the action state value Q value. It needs to take the state and access put into output value. At the same time, it on a replay buffer and target network in DQM, and the soft update method for target network. There are 4 neural networks in the algorithm: policy network, value network, target policy network, and target value network. And in the common RL training process, there is a greedy strategy to balance exploration and exploitation. Similarly, the Uhlenbeck stochastic process is used in DDPG as the random noise introduced. The UO process has a good correlation in time sequence, which can enable the agent to explore the environment with momentum properties. The purpose of exploration is to explore potential potential better strategies. Therefore, during the training process, we introduce random noise to the action decision making mechanism. This is a chart of reward trend with episode. The blue line is return and the red line is average return to better see the convergence trend. The last part is application of reinforcement learning. The following are some applications of reinforcement learning. The first one is application in autonomous vehicle. Reinforcement learning can be applied in autonomous drive tasks such as trajectory optimization, motion planning, dynamic path controller optimization, and scenario-based highway learning strategies. And the second one is robotics and industry automation. In industry enhancement, learning-based robots are used to perform various tasks. The use of deep learning and reinforcement learning can train robots with the ability to grasp various objects, even objects that are invisible during training. And the third one is application in China finance. Simple models can be used to predict future sales and predict stock price. Inter-reinforcement learning, the IL agent can decide to perform this task, whether to hold, buy, or sell. And the first one is text, voice, and dialogue system. And the company collected a large amount of text and found use through tools that unlock the unstructured text. Deep IO is used to object text summaries. IO is also used to allow chatbots to learning from user interactions, thereby helping them to improve over time. The fourth is application in healthcare. In terms of healthcare, patients can receive treatment from policies learned by the IO system. IO can use previous experience to find the best strategy without previous information about mathematical model of biological systems. And the last one is reinforcement learning in games. Through reinforcement learning, AlphaGo Zero decides how to go according to the current chess game. It relies on the simple trees and search of the single neural networks to evaluate the position movement and the sample movement. Okay, the above is all my report. So thank you very much.
Thank you very much. That was a very interesting report. So let me say a few words and comments about it. So there were two parts. First part is about the list of algorithms. So actually, the aim of all reinforcement algorithms is to do the same thing, to enable a RL agent, reinforcement learning agent, to learn faster and better in any kind of environment. So now we can have a look at the applications of reinforcement learning. The environment is actually a place where reinforcement learning can be applied. And you can see that there are several applications related to games, which is the most natural way to apply reinforcement learning. You know, there was a big story that that a computer won a champion, won a chess play with the champion of the chess in the world, and that was a very big news, and that was a proof that artificial intelligence in some way can perform better in specific tasks than a best person in the world for this task. But actually, this is not enough for artificial intelligence to be really artificial. What we need is the algorithm that will be able to learn how to solve any kind of problem or arbitrary problem by himself. So the artificial intelligence becomes artificial when you give him a task that he does not know how to solve in advance. He was not pre-trained, so it's not kind of supervised learning, and he has no prior knowledge about this task, so it's not kind of unsupervised learning. But the algorithm starts to learn by itself in the environment by exploring different ways how to improve itself. It's like a human being. So the idea of reinforcement learning is that you can give a reinforcement learning algorithm, general idea, any kind of environment, such as game Go, or you can give him environment for trading on financial stock, or you can give him environment how to drive a car, and eventually it will learn how to do it better than a human. But that's a general idea, and under this we could find a lot of problems, such as well as for the explainable artificial intelligence, curse of dimensionality. So the world, the real environment, the real world is so complex, so that there are a lot of variables and numbers to describe the state of the world. Yes, you can imagine while you're driving a car, you have a lot of things that you need to care about when you drive a car. And actually the human brain is very complex and very efficient in it. But yeah, and also the action space is very big. And if we consider multi-agent systems, when we have a lot of agents interacting with each other, it's also a big problem for reinforcement learning. Another problem for reinforcement learning is the learning speed. So of course, if you also there is a very interesting application that was not mentioned in this report, which is related to the actually well known, actually maybe next month we will add information about it, is when a model of a human learns how to walk. I think that's a very classical example of evolution. So the reinforcement learning agent can learn how to walk much faster than a human. And we can see, and later on we will try to find some examples. Next month you will see that the result of it, the optimal behavior of optimal walking strategy of the robot, is actually the same as the optimal walking strategy of a human. But human needs some maybe 1 year or several, so he needs much more time to learn how to walk, but the robot can do it by his own. So reinforcement learning is a fundamental basis of this kind of real artificial intelligence. When you can give an algorithm some general problem or any kind of specific problem, and then in this problem he will learn by itself how to do it. But of course, a lot of problems in this direction we have now, and I hope next presentation will. In the next presentation, you will see some specific applications and specific directions that we are working now. So thank you very much. So the next.
Okay,
speaker, thank you. So the next speaker, let me share the screen. The next speaker is Sun-Tzu Shi. So he is a PhD student, and also this is a joint presentation with Ivan Kondratov. He's a master student of mine. And the title of the presentation is The Reinforcement Learning for Resource Scheduling. So why resource scheduling and why reinforcement learning? So Sun-Tzu Shi, you can start to share the presentation while I'm explaining the meaning of it. So the scheduling problem is actually a very wide problem for the yeah, you can start sharing the screen. You're not sharing the presentation, you're sharing myself. So the scheduling problem is a
hello.
problem. Yeah, hello. Is a problem where we need to construct an optimal schedule for the tasks or job in some process. This kind of process can be related to project management when we have a lot of production teams, a lot of groups of people working on different, for example, a factory or IT systems, where they need to and our task is to schedule their resources to understand how better to schedule their work in order to improve the efficiency and so on. Another application is application related to computing clusters. So as far as you understand, currently most of the computing in a company is done in the big clusters with several computing machines involved and so on. And there it is very, very important to schedule their schedule and assigns jobs and tasks within this system into different machines, because the running time of a machine takes a lot of money, the electricity to run the machine, then cooling systems to cool down the machine. So we need to try to optimize it. Also, we can even consider a case when you need to schedule tasks in your computer device. That's a very, very low level scheduling task, but it's a very important for your computer to work fast. So you need to have some scheduling. This type of application of reinforcement learning is a little bit far away from artificial intelligence, actually, because but it's a kind of direction for application reinforcement learning for optimization, where we need to optimize schedule when we need to do this kind of things. Okay, so Sun Tzu, yeah, and by the way,
hello, Professor.
But by the way, in this presentation, we will our target again is to focus on high dimensional case, where we have a lot of jobs and a lot of tasks that we need to schedule. Yes. This is a big challenge for our direction, and here we will present our first results and ideas for it. So Sun Tzu just started his work in September.
Okay.
So, yeah. So thank you very much. Thank you very much.
Okay, Professor. Hello, everyone. My name is Sun Qiu Shi. The topic of my presentation is workflow scheduling using neural networks and multiple agent reinforcement learning. There are three parts of my presentation. First, I will introduce the background. What is multiple agent reinforcement learning? We will start it from single agent model. It's like a picture here. The main idea is to train the agent in the environment. The agent make an action, interact with the environment, and get a reward as feedback. And then with this experience, the agent can improve its policy. And then we want to train an agent that can obtain the optimal policy and maximize its returns. And for multi-agent reinforcement learning, there are several agents in the environment, and each agent can make action. So here is our joint action interact with the environment, and agent here, they can play against with each other, or they can play cooperate with each other. Both, and here are some notations. Next question is workflow scheduling problem.
Could you please comment?
Hello? Yes.
why we can need multiple agents. Why we need multiple agents? Because now it's more related to game theory as well, right? So why multiple agents, and what is the meaning?
You mean why we want to use multi-agent to solve this problem?
Why usually people want multiple agents? What case is?
Because yes, because the multiple agent is much more similar with our real world. Yes, in our real world environment, there are in most cases in most cases there are multi-agent, not a single agent. And I think this is the reason why we want to use multi-agent model.
Yeah, yes, general, yes. Also, I can say that in a very complex type of systems, where not in the nature, but in some engineering systems, when we have a lot of kind of nodes or a lot of processing units where that needs to make a decision, it's a kind of where we have a lot of subsystems that need to take a decision, we can try to model it as a kind of multi-agent system, where we think that each agent needs to know by himself what is the best way to do it. So we do not have one central controller for the system. No, we train each subsystem to work by itself, and then in order to maximize some joint efficiency and so on. So the multi-agent reinforcement learning works in the same way. We have a lot of agents, and they're producing. They are trained together or independently. But the idea is that they implement tasks, or they apply their actions and policy independently in order to receive some different. We have different goals to improve the joint reward. If this is a kind of one system, then, for example, it's one scheduling system, we need to improve make span or improve scheduling for the whole system with different using several scheduling nodes. Or if it's a kind of simulation task, when we need to simulate of how some system will evolve in the future, then we just do some individual, each agent has individual rewards and so on and so on. Okay, so that was kind of introductory for this. I think this is important. Okay,
yes.
Please continue.
Okay, recent years we have witnessed the breakthrough of deep learning techniques in different industry fields, such as machine translation, speech recognition. So many large companies, they have developed their own clusters with expensive GPU server for their AI-driven service. And in this case, efficient resource scheduling is crucial in operating a cluster with multiple training jobs. And there are two kinds of schedulers in today's deep learning. In today's deep learning cluster. The first is the general proposed cluster scheduler, such as Google's BERG, Microsoft, and Tencent's Yarn. They use the strategies first in, such as first in, first out, dominate resource fairness, and so on. The Google's BERG, the structure is like this picture, and these schedulers, they allocate the resource according to specific rules and do not adjust resource allocation during training. And the other methods is white box heuristic cluster scheduler. They use the strategies supervised learning methods. We know supervised learning models, they require a deep understanding of the cluster frameworks and workflows. the well-trained model is tightly coupled with the framework implementation. For example, if there are some change in the cluster, the well-trained model cannot perform well. Next section is the project. Here is our focus. We try to modify the existing or develop new approaches in a multiple agent reinforcement learning setting to get the scheduling workflows. And the structure is like the picture below. And our object is to optimize the workflow completion time and the utilization of the system. Then I will introduce the environment of our project like this. Workflow, the jobs arrive as the cluster with the Poisson distribution, and the state of our environment state space is imaged as follows. I will introduce. We can see is a state representation with two candle resources, CPU and memory in our cluster. And there are 3 pending job slots. Here in our cluster, the different color means different jobs. For example, the red job here means it needs 2 units of CPU and 1 unit of memory for the next 3 time step. And the job in cluster means it's scheduling now. And the job in our job slot, we can see the source requirement of the job. This is the job which are waiting for scheduling. And in backlog is the job which are out of job slot. And here we can only see the number of the job waiting here. And the grid number of this state is like formula like this. For the capital T is the length of time step, and capital M is the number of job slot. C is the unit of resource in cluster. In our example is 3, and B is the number of our backlog here. We can also say that this is a dimension of our state space. And here is the action space for each agent, where A equal to I means schedule. Oh, sorry, this is wrong. It's not job. A is action. A schedule job at S slot. And here phi means it's a Y the action. If A equal to phi, it means we do not schedule the further job. Then the agent do nothing. And next is the reward of our environment. This is the formula of reward at each job step, where Tj is the duration time of job J. The duration time consists of completion time and the waiting time of the job. Completion time is the job which from the time step start to execute until it has complete. And here is another index slowdown. The formula like this, and the Cj is the completion time of job J. Our object is to maximize our reward and to minimize the slowdown. Yes, and for our project, there are challenges because we want to build a model that would be able to work with the large amount of jobs. So there is a large state action space. As we know, the Go game, the grid number of Go is 361, and the state space complexity of Go is this very large number. But in our case, the state action space is much more larger than Go. Then how can we overcome this challenge? Then here, yes, we get idea from other papers, priority group, and heterogeneous agent. It's a method from this paper is for taxi scheduling problem. In this paper, they regard each taxi as agent. So we know there are maybe thousands of agents in one environment, maybe. But they divided the area into different regions, and taxi in the same region, they act the same. So we can regard the agent as one agent. So with this method, we can reduce the number of, we can hugely reduce the number of agents. With this method, we have two ideas. The first, okay.
Yeah, so I want to add some words about this. I like to use some intuition examples to explain most of the concepts in reinforcement learning, but it doesn't depend on the field. So, so the problem of this paper is that we have a lot of taxi drivers, and we want to use reinforcement learning system to recommend the taxi driver which region to use on the map in order to improve the efficiency of the taxi service, such as taxi. Every one of you have used a mobile app with the taxi service at least once, and sometimes you have a problem that you're waiting for the taxi a lot of time. The problem is that there are not enough taxi drivers in your specific region. So how to solve this problem? We need to recommend a taxi driver to go to a different region, and but the problem here is that the number of taxi drivers in the city can be of a very big number, right? And if we want to use reinforcement learning, then we can try to construct different types of the models. And in this paper, what is recommended is to divide a region of the city, the city map into several regions, and then to consider in each specific region a number of taxi drivers as one agent. Why as one agent? Because their state and action space is the same, because the state space in this model is constructed as a number of taxi drivers and demand for taxi in his region and regions around them. So in some sense, all taxi drivers are equal, are the same in one region. So for us, for reinforcement learning, it means that the learning of agents which are located in one region is equal to learning of one agent. And that's an idea of heterogeneous agents, that if we can represent 100 agents or 1,000 agents, actually it's a one agent. If they're unique, if they're identical, then the learning speed for them will be much faster, much faster. So that's one way to solve this problem. And actually, you can use the following interpretation of this process. So maybe it is not perfect, but anyway, you can you have 100 children that you need to teach in the school. So if you give each individual children a teacher, then you will need 100 teachers. Or if you have only one teacher, or maybe if you have 5 teachers, means a computing resource, you have only 5 computing resources, then you will need to train first 5 for one child, then again 5 or one child, and again and again and again. That will take a lot of time. That will take, yes. And therefore, what we do is we separate children into the classes, into the groups, and for each group we have one teacher. This is a kind of heterogeneous approach. So we we judge everyone as the same, as equal, and we give them the same tasks, we give them the same home tasks, we give them the same lectures, we can and therefore we reduce the learning we reduce the learning speed for all of them. So that's a kind of very similar idea. Okay, thank you, Sun Sushi. Please continue.
Yes. Okay. First, the idea is to group the jobs with their priority, and where agent are the groups itself. And the second idea is where the agent are jobs, then we can consider each job in one priority group as a heterogeneous agent. And this is Professor you just teach us now before. And here is our example. It's based on a paper. It's based on this paper. We evaluate a single agent reinforcement learning model with the policy gradient method. And the environment is the same as I introduced before. And here, we, for the grid number, we have it did not very big grid number. Here we can see is the objective of policy is to maximize the expected cumulative rewards, and the gradient of the objective is given by like this. Here is the structure of our model. It's reinforcement learning model with our policy represented by DNN neural network. And here is our result. We trained the models on platform Google Colab with the library Sino and Lasagina. It took over 8 hours for training the agent and over 1,000 episodes. Here, the result improves the total reward here, discounted total reward, and slowdown as well as the slowdown performance. And we can see here the right line and the blue line is our policy gradient method. And this green, light blue, and yellow line is method SJF, small job first, and Tetris and random. Because these strategies are all general purpose cluster scheduler, so we can see in different iteration they perform the same as a straight line. Because they just use rules to schedule the jobs without training the model. And for our further plans, first we want to build a multi-agent environment which based on high-level scheduling with priority groups and with novel rewards mechanism that depends on various factors. And the second, we will research approaches to handle the large action and space to test specialized algorithms such as mean-field approach and Impala, and also develop action state space with parameterization technicals. And that's all. Thank you.
Thank you very much.
Any questions?
Thank you very much. Actually, we have started this direction I think at summer, and currently what we are doing is we are starting to try to solve a large-scale scheduling problem. And for the large-scale scheduling problem, we can use several different methods. And one of the methods that we are interested in is to introduce a multi-agent environment where each agent will be an individual scheduling unit. And this means that we can reduce the dimension of the problem significantly. For example, using the approach of that was described in the paper about the taxi system, and we could use the approaches. And there we can consider as an agent a priority group where the idea is that we will only control the priority group. Yeah. And another way is to consider each job as an agent, and then we have a big number of agents, maybe thousands of agents, and then we can need to handle this situation using kind of mean field approach. But all this, I hope that we will present next month. Okay, thank you very much, Suntsushi.
Hello, everyone. My name is Alexey Belashapka, and I would like to present my research on box shape object detection and pose estimation with neural networks and point cloud fitting. This is a very practical research that aims to automate transport container logistics at a production plant. The task that I investigate is to detect these KLT bins that you can see on the images. These KLT bins are typically used to store or transport goods from one point of the production plant to the other. In order to be able to grasp them with a mechanical hand, I have to provide a rough pose estimate, a rough estimate on the location of a KLT bin in the 3D space. There are several use cases that can be considered. In my research, I concentrate only on two of them. The use case when the camera observes the KLT bin from the top, or the use case when the camera observes the KLT bin from the side. The solution incorporates this pipeline. First, we continuously scan the environment by capturing the color depth images. These images are processed with the Masker CNN network that generates the bounding box region and the segmentation mask for each bin that it detects. Then these regions are processed with plane fitting algorithm to estimate the final pose. The final pose is 5 degrees of freedom with 1 rotational degree of freedom missing. Let's consider the first step, capturing the images. The color depth images are captured with an Intel RealSense camera that you can see on the top of the slide. This camera provides color images like this one on the left, and also depth image. A depth image can be visualized as a colored 3D mesh, and you can see such visualization on the right image. Having a color image, we perform a so-called instant segmentation task. For this, we use the Masker CNN network. This network detects all the relevant objects, and for each object, it creates a bounding box rectangle, as you can see on this third image. And also for each of this region, it predicts the segmentation masks, like on the fourth image. We are especially interested in the segmentation masks. To train such a network, we label a lot of images of KLT bins, which we then place on a random industrial background. This is done to ensure the detector robustness and to avoid overfitting. On this slide, you can see the performance values of the Masker CNN. The segmentation accuracy is measured with the mean intersection over union metric. The values are quite close to 1, which is very good. Usually these values are much lower. The biggest problem is that for horizontal view use case, we have a lot of bins that were not detected. Below you can see a sample image that shows this problem. It contains 3 KLT bins. You can see that the left one and the middle one were successfully detected, while the right one wasn't. This shows that This problem is actually quite difficult for neural networks because the KLT bins do not usually have enough texture or some reliable unique features on which the network could rely. And also they are very similar to the environment that they place to. Having these bin regions generated by Maskr CNN, we can continue with the pose estimation. The pose is estimated from the depth image that is provided from the camera. For this depth image, we use a point cloud library to estimate all the planes that are on this depth image. Then for each bin that was detected by Maskr CNN, we pick the closest plane to that region and assume that this is the pose of a KLT bin. For example, for this gray KLT bin on the image, we would take the green plane that belongs to its frontal face. This gives us a 5 degree of freedom pose because it creates for us the central point of the face and also a normal vector of this face. We miss one rotational degree of freedom, which is the rotation around the normal vector, because plane doesn't have any kind of orientation. To estimate the plane fitting algorithm accuracy and precision, we compare it to another state-of-the-art algorithm for pose estimation that involves checkerboard pattern tracking. To do so, we print this checkerboard pattern on a planar surface and then put a KLT bin on top of it. So we can estimate the KLT bin pose with plane fitting and also the camera pose with the checkerboard pattern. This checkerboard pattern should, in general, provide a camera pose with a very high accuracy. But unfortunately, at the moment, the checkerboard detection algorithm doesn't work too good. The preliminary precision of estimate of the plane fitting algorithm is around 3 centimeters. We hope that we can lower this value once we refine the implementation. Future directions could be to resolve this issue with the pose estimate evaluation approach with the checkerboard pattern. For this, we could integrate our special procedure called bundle adjustment that optimizes all the camera poses that are related to a single checkerboard pattern. Also, another direction of the research could be to make the Maskr CNN run faster, to have more estimations per second. This involves, for example, switching the backbone network, because originally Maskr CNN was based on a very large network, ResNet 101, with 101 layers. Switching it to MobileNet should make the Maskr CNN network faster, but probably less accurate. Also, this involves tuning the network happy parameters. And the third option to continue the research could be to integrate to the system advanced 3D surface reconstruction algorithm like BED-SLAM. This could enable easy labeling of the data sets, or for instance, point cloud refinement, so that the point clouds that we obtain from the camera, they can be less noisy, and then we can estimate the poses with plane fitting with higher accuracy. Thank you for your attention. If you got interested with this topic and have some questions, then you can reach me via the email. You can see the link on the slide.